Continuing with enthalpy changes in regards to reactions and how we can calculate that. So although we cannot measure the actual enthalpy or energy change of a substance, you can measure the change in enthalpy. And that's what we're going to be looking at today, one way to measure that. The change in enthalpy for reaction is called the heat of reaction. Other teachers are texting me while I'm teaching. Like I'm probably one of the only ones that y'all still having to do stuff. I know. This will be the last, no, tomorrow Hess's Law. It's fun. It's like a puzzle. I think it's like a puzzle. Y'all probably may not think that. All right. So we know that the triangle means delta. We've used that already. So heat of formation, which is represented by my delta H of formation. We talked about that yesterday. This little superscript 0 means not, NaUGHT, which just tells us that we're at standard conditions. And that's how anything that we're going to be working on are going to be. Sometimes in AP or college chemistry, you may have some changes. So it is the energy need to form 1 mole of a compound from its elements. So that would be like if I had hydrogen plus oxygen gives me H2O liquid. That would be an example of a heat of formation reaction. Water is my compound, and these are the way that those elements usually exist. It's their standard way to exist. The delta H of all elements is going to be equal to 0, and this includes diatomics. So you have like a reference sheet that you picked up today that just was a table with a bunch of numbers. That is delta H of formation for different compounds. You don't see any diatomics or any elements listed on that because they're already formed. It doesn't take energy to form them, so their value is 0. So those values are usually in a thermodynamic table or given to you. That's what you had, the table that I've given to you, because you'll need them on some of the practice. When you're getting those values, be careful because, for instance, water, you don't need to write this. Water can exist as a gas, as a liquid, or as a solid. So that's why on a thermochemical reaction, you have to have what state it is in, because when you get a value, a delta H value is going to be different for what state that they're in. So just be sure that you grab the right state if there's multiple things listed. So to find the heat of reaction, the overall heat of reaction, you're going to use your heat of formation for the compounds that make up that reaction. And that formula is going to be the summation of our products minus the summation of our reactants. All that E means, it just means summation. So I'm totaling up all the values of the products, adding them together, and then subtracting the total amount of the reactants. N, like we've done before, stands for moles, and we'll be able to get that very easily by just looking at the coefficients. If it happens to be a combustion reaction, which remembers is just a reaction where something's burned in the presence of oxygen, usually hydrocarbons, to get some kind of release of energy, then it's going to be the same procedure, but you're just going to be solving for the delta H of combustion. But it's still going to be the same thing, summation of products minus your summation of reactants. All right, so let's look at one and it'll make a little bit more sense. All right, so this is my equation. I'm trying to find the delta H of reaction for this equation. These are the delta H of formations for the different compounds that are in that reaction. Notice that oxygen is not listed because it has a 0 value. So the more elements or diatomics you have, the easier the problem is going to be, because those you don't have to really do anything with. Remember, those elements of those diatomics, it did not take or release energy to form those, so they don't have a heat of formation. All right, so I'm going to start with my reactants. So my first one, I'm going to do CO2. So I'm going to do 5 because it has a coefficient of 5. And I'm going to multiply that by its heat of formation, which is negative 393.0. And then I'm going to add to that my next product, which is water. So 6 times my water value, which is negative 285.8. And then that's all of my products. So that's the summation of my products. And I subtract from that the summation of my reactants. Well, in this case, we only had one reactant that mattered and it didn't have a coefficient. So I would simply subtract 145.7. That's the only reactant I had. So that is everything that goes in your calculator. And remember, the signs do matter, whether it's positive or negative. So be careful with your signs. So give it a try in your calculator to see if you can get the correct value. As far as Sig Figs go, remember, we're either adding or subtracting. So we're looking for places behind the decimal. So since all of these values had one place behind the decimal, you would want your answer to have one place behind the decimal. So what did we get for our answer? 3,534.1 and a negative, correct? And my units are always going to be the same as these units that I use. So it's going to be kilojoules per mole. So that is an exothermic reaction because it has a negative value. Trouble getting that in the calculator? They're probably doing Hess's law. They're already that excited. I don't think they're going to ever put you in a calculator.
I got last place.
I think they're going to put you in a calculator application. Do you? Five times negative 393, close my parentheses, and then add it This. Y'all are better at calculators than me. I'll do it a different way. Yep. That's probably what happens. All right, did you get it? All righty. All right, let's look at one more and then y'all can practice one. So just this reaction, looking over it, do you think it's going to be more work or less work than the one that we just did? Got a more? Yes, because this and this are both elements in their normal state. So those are zeros. So I don't even have to worry about those. And if you ever forget that, if you go to your sheet, you start trying to find just FB on there, it won't be there. So, and these don't even have coefficients. So I just have to do my delta H of reaction because this is not a combustion, would just be my aluminum oxide because that is my product. So -1676, that's my total, and subtract from that my total of my reactants, which is my iron oxide. And those values did not have any place behind the decimal, so my answer would not have any place behind the decimal, or any places, I guess would be a better. All right, what did we get for that one? Perfect. -850, and your units, remember, just grab them from over there, kilojoules per mole. All right, the next one I'm going to let y'all try is a little bit different in that you're going to have a different X. Notice that you're looking for your delta H of formation for this compound. Once again, I don't have to worry about oxygen. So I know my whole reaction. So I already know my delta H of reaction. So -2219.2 is going to be equal to. And then you start from there. You have everything you need for your products. And this will be your X because you don't have that information. So it's just a little bit different as far as your algebra procedure would go. So the answer is negative 103.0. So I'm not for sure where you got that little one. That's weird. All right, well, let's just work through it. So we'll see. All right, so my carbon, I know I can already tell them. Group myself. All right. So we have negative 2219.2. That's my delta H reaction. So I'm going to start with my CO2. So that's going to be 3 times negative 393.0. Add that to my water, which is 4 times negative 285.8. That's all of my reactants, and I subtract from that, I mean, all of my products, I subtract from that my X, and I only have 1 mole of that. So that becomes my X. Were your numbers all the same as mine there at that point? So when you put all this in, you get, I got negative 2, 3, 2, 2, and then it still would be your minus your X. So then when I bring that over and I solve for my X, I end up getting X is equal to negative 103.0 kilojoules per mole. Was it 0.1? I don't. Do, let's see, tell me I'm lost. We're at. Oh yeah, I didn't know. I should have. I don't know why I did that. I don't know why I did that. So you still got the negative 103. Okay. So I guess it didn't matter. But yeah, you're right. This should have had this should have had 0.2 somewhere. It just sometimes can be a lot of numbers and keeping them organized. Hess's law, as far as putting stuff in your calculator, is definitely. So y'all have some time to practice on this, or you can practice on your things from yesterday. What to? And we will do one more new topic, and then we will call it a year. Call it a school year.